Hi, everybody. Welcome. We're going to talk about exponential patterns. So let's say, I'll have you take a look at this paper. Just read this to yourself real quick. Folding a sheet of paper into two parts. So when you don't have any folds, it's just a piece of paper. When you fold it once, you have two rectangles that are formed. When you fold it again, you have four. And if you're not sure, just think of a piece of paper and actually fold it. If I fold it once, then I have two rectangles, right? It makes a seam, etc. So you can fold your paper to see how that works. If I fold it again, I have 8 rectangles, etc., etc. And it just keeps going. So we want to try to find a pattern here so we can come up with our exponential equation. So 1 is just 1, 2 is 1 times 2, 4 is 1 times 2 times 2, and then this is 1 times 2 times 2 times 2. And then we just keep going. So notice the pattern here. I have 1, 2, then I have 2 2s, and then I have 3 2s. So on this next one, if the pattern continues, I would have 4 2s. So that's 4 times 2 is 8 times 2 is 16. If you were to fold your paper, you would see that that's true. So it keeps going. And so this, if you look at a power of 2, 1 is 2 to the 0. This is 2 to the 1. There's only one of them. This is 2 squared, 2 cubed, 2 to the 4th, etc. So for x, it would just be 1 times 2 to the x. So my equation is 2 to the x. This is an exponential equation, which is what we're starting on. So if you want to find it after 10 folds, you put in x. Instead of x, you put 10. So 2 to the 10th, get your calculator. 2 to the 10th gives me 1024. So 1024. All right, if we wanted to graph this, we want to go ahead and put some points in. So let's go ahead and graph the 2 to the x. So let's do some negatives and 0 and some positives. So 2 to the negative third is 1 over 2 cubed, which is 1 over 8. This is 1 over 2 squared, which is 1/4. 1 over 2, which is a half. And then 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. Okay, so we're going to graph these points. So at 0, I'm at 1. And then at 1, I'm at 2. 1, 2. And at 2, I'm at 4. And then obviously at 3, I'm at 8. Then I go over here at -1, I'm at a half, eighth, etc., etc. Now I want you to think about this for a minute. This is getting smaller and smaller. Do you think it's ever going to be 0? Hopefully you think the answer is no, because it won't. So won't ever reach y equals 0. So that means that's something called an asymptote, where a graph approaches but never crosses. Okay, so this has a horizontal asymptote. We'll talk more about this in a little bit. Asymptote of y equals 0. Okay, so with exponential functions, we'll talk about the properties in a minute. They have horizontal asymptotes, and y equals 0 is the asymptote. All right, so we're going to graph one more. So why don't you pause the video for a sec and try plugging in points yourself. So you can plug in negative points. I'm just going to plug in a -1, 0, 1, 2, and 3. Okay, why don't you pause, plug those in. All right. 1/2 to the -1. This makes it a 2 times 8 is 16. That's a big number. I don't really want to graph that, but we'll kind of estimate it. And then 1/2 to the 0. Well, 1/2 to the 0 is 1 times 8 is 8. 1/2 to the 1 is 1/2 times 8 is 4. 1/2 squared is 1/4 times 8 is 2. And then 1/2 cubed is 1/8 times 8 is 1, etc. So let's graph this. So at 0, I'm at 8. And then up here, I'm at 16. That's huge, something like that. At 1, I'm at 4, 2, 2, and 3, 1, 2, 3, 1. So this looks like that. Okay? All right. Later on, we're going to talk about what these mean, because when it's going up like this is called growth. Well, we'll just talk about it real quick. This is called growth, but when it's getting smaller like this, it's called decay. And we'll talk about how you know for sure which it is just from the equation. All right, go ahead and flip. We're going to finish up the other 2 problems, and then I'll pause, I'll stop the video, and I'll make another one for the rest of it so it's not so long. Okay, I'm going to remove this. All right, sweet. So now we're on the back. Let's go ahead and read problem 1. All right, hopefully you paused this and read it. It tells you that the monster's height triples in size. And it says you assume that he's 1 foot at birth. So this is your initial. So it's how much you start with. So at time 0, you start with 1. That's the initial. Okay? And then it triples. So after 1 hour, it's going to multiply by 3. So it's going to be 3, right? And then it's going to triple again, which is 9. And then it's going to triple again, which is 27. So see the pattern? This is 3 to the 1, 3 to the 0, 3 squared, 3 cubed, etc. This one's going to be 1 times 3 to the 10th. So this is just 1 times 3 to the x. Okay. Same thing over here. Go ahead and read this. Give you a sec to read it. You should probably pause it because I'm not going to give you that much time. Okay, I'm back. You start with 5 inches and it's quadrupled every hour. So before it quadruples, it starts at 5, and then it's going to quadruple, and then it's going to quadruple again, and quadruple again, etc. So hopefully you're kind of seeing the pattern here. So for exponential functions, this is always the form. Always the form. And what does all of this mean? The A is your initial amount, it's how much you start with. And B is the growth rate. Now, growth is when your B is greater than 1. Decay is when B is less than 1. And I showed you over here on this graph, this is decay and this is growth. So look at your B. Here it's 1/2, so it's less than 1. So that's why it's decay. Here it's 2, which is greater than 1. That's why it's growth. Okay, so it's growing. If it's a fraction, it means it's decay. All right, so take a look at these and tell me if you think it's growth or decay. Write it on your paper, pause the video, and then come back and we'll double check. All right, welcome back. We basically want to look at B. That's B. Okay, so we want to check to see if it's greater than 1 or less than 1. So this is greater than 1, so it's growth. This is less than 1, so it's decay. This is less than 1, so it's decay. This is greater than 1, so it's growth. I think I'm actually just going to keep going on this video. It hasn't been too long. All right, not too bad. Hopefully that makes sense to you. All right, flip to the next page. So talking about this, we already talked about an asymptote when I did that first graph with you. This one right here. We talked about how it's getting closer but never touching, right? A horizontal asymptote. I explained that a little earlier. So y equals 0 is an asymptote where it approaches but never actually reaches it, okay? So we have our formula here. Now, for doing this in the real world, we want to talk about usually populations. We can talk about like carbon decay. We also can do stuff with interest, compound interest. There's a formula for that later that we can talk about. But usually it's some kind of population or cells splitting or disease. Those are usually modeled with exponential growth and decay. All right. I don't know if you guys remember at the beginning of the pandemic, they talked about the exponential growth of the virus because if you have it and you're around somebody, then those people are around other people and those people are around other people. It becomes this exponential growth. So COVID is a great example of something that can be modeled with exponential growth. All right. When we're talking about real world problems, this is always your initial amount of whatever you have. So the initial population, the initial bacteria, the initial whatever. And this is the rate of growth or decay, obviously, if it's less than 1. And this variable up here is the number of time periods passed. So that can be in days, it can be in years, months, etc. It can be in lots of different time increments. Okay. Now, to know if it's growth, to figure out your B for growth or decay, when it's growth, you take 1 plus whatever the growth rate is. When it's decay, to find B, which is my rate of growth or decay, you take 1 minus the rate. Okay? So these are really important for you to figure out B for the exponential equation. All right, let's look at this first one here. We have write an equation to model the population of fish. So it's population problem, very common. Initial population is 600. Okay, well, initial population is 600. That's my A, right, in this equation. So I already know A. Awesome. Then it says it's growing at a rate of 6%. So that's 0.06. So because it's growth, it's going to be 1 plus R for my B. Sorry, that's a little messy. So there's your B. So now I know B. So I can plug everything in here. So Y equals 600 times 1.06 to the X. Common mistake people make is they just put 6 here, thinking it's 6% or 0.06. But you can't just put the rate. You have to either add it to 1 or subtract it to 1, depending if it's growth or decay, to find your actual growth rate. Okay, the B. All right, why don't you guys try this next one? Pause the video and then come back and join me and let's see if you did it right. Welcome back. It's fish again. Yay. Starts at 10,000. That's my initial population. So that's going to be A. It's what I start with. This time it is decreasing at a rate of 15%. So 15%, do 0.15. So because it's decreasing, I'm going to do 1 minus R because it's decreasing. Okay. On this one, it was increasing. So 1 minus 0.15 0.15 gives me 0.85. So now I have everything I need to put into my equation. So there's my exponential equation. Now it says here, what will it be in 5 years for each of the models? Okay, so that means X is 5. So I'm going to take my first model, and that's what people were doing with COVID and all kinds of populations and, talking about like global warming and, the landfill, how much space is going to be in the landfill and your carbon footprint. And when you put something in the landfill, how long does it take to decay? There's all kinds of equations that model it. And so they use that to make predictions. And that's what we're doing here. We're making a prediction in 5 years, what's going to be the population. So instead of X, I'm going to put 5 in each of these and see what I get. And this is really common. A lot of times there's different models based on data. And then you use those to compare the prediction to see which model kind of makes the most sense. Or a lot of times people use whatever model is convenient for what they want to tell people. There's a lot of manipulation of data, sadly. So 1.06 to the 5th times 600 is 802.94. And then this one, let's see, 0.85 to the 5th power times 10,000 gives me this. So there you go. There's your population with both models. All right. Good luck on your homework. Thank you.